Hey everyone! In this video, we're going to continue talking about L'Hopital's rule, but this time we're going to be taking a look at how to use L'Hopital's rule when we have other indeterminate forms. So remember, L'Hopital's rule, we can use that to help us evaluate a limit when we have an indeterminate form of 0 divided by 0 or infinity divided by infinity. Now, we have other indeterminate forms that aren't those two. In this video, we're going to be taking a look at 0 times infinity and infinity minus infinity. So what we have to do is if we have one of these two indeterminate forms, we have to do a little bit of rearranging, a little bit of algebra, so that we do end up with 0 over 0 or infinity over infinity, and then we can actually use L'Hopital's rule. So let's take a look at some examples and talk through them. And as we go, I can explain a little bit more about what we're looking at. So my first example, I had the limit as x approaches 0 from the right of x times the natural log of x. So the first thing, just really quick, if I try to evaluate this by just plugging in 0, what I'm going to end up with is 0 times the natural log of 0. The natural log of 0 is actually undefined. If we were to take a look at the graph of this, as I approach from the right, we have a vertical asymptote at 0. So the natural log becomes unbounded as we approach 0. So this limit is actually 0 times infinity. So this is another indeterminate form, but this is not one that we can use with L'Hopital's rule. Remember, we want it to either be 0 over 0, or we want it to be infinity over infinity. So what we're going to want to do, right now we have two functions that are being multiplied together. We're going to want to rewrite this as a complex fraction. So either I can write this as f of x divided by 1 over g of x, which this would simplify to what we started with, or we can go the other way, and we could write this as g of x over 1 over f of x. And again, this would simplify to what we started with. Written like this, though, we have our fraction, and we should end up with something that is 0 over 0 or infinity over infinity. Now, the one that you want to choose, you can use either one, but oftentimes there's one that's going to be easier to find the derivative of. So in our example, I have x and the natural log of x. So I'm going to rewrite this as the limit as x approaches 0 from the right. And I'm going to put this as 1 over x. So the natural log of x divided by 1 over x. So as you can see, dividing by a fraction is the same as multiplying by the reciprocal. So this would simplify to what we started with. But written like this, we have something that is an indeterminate form. If I plug in 0 into the numerator, again, this is unbounded, so this would be infinity. And then 1 over 0, same idea. As you approach 0 from the right, this also becomes unbounded, so we have our indeterminate form of infinity over infinity, which is what we're looking for. So now we can take the derivative of the numerator and the denominator to use L'Hopital's rule. So the derivative of the natural log of x is 1 over x. And then we want to take the derivative of 1 over x, which this is the same as the derivative of x to the negative first power. So using our power rule, the negative 1 will come down, and then we have x to the negative 2. So that's going to be negative 1 over x squared. So rewriting our limit, using our derivatives, the limit as x approaches 0 from the right, now we have 1 over x, and then that is going to be over negative 1 over x squared. So now let's do a little bit of simplifying with this before we try to evaluate. So 1 over x, dividing by a fraction is the same as multiplying by the reciprocal, so negative x squared over 1. And here we can see that we have some x's that are going to simplify. So you have 1 on top and bottom that will cancel out. So I'm going to be left with a negative x. So what we're looking at then, the limit as x approaches 0 from the right of negative x, and here we can just plug in 0, and we get our limit is equal to 0. So that means all the way back here at the top, our original limit, because we were able to use L'Hopital's rule, this limit is also equal to 0. So that's the first one. In this case, we ended up with an indeterminate form of 0 times infinity. We were able to rewrite our expression in such a manner that we have one of the two indeterminate forms that we can use L'Hopital's rule with, take the derivative of the numerator and the denominator, and we can find our limit. Let's try one more example. This one is a different indeterminate form. So in this case, I have the limit as x approaches 0 from the right of 1 over x minus 1 over the sine of x. So if I were to plug in 0, I'd have 1 over 0 minus 1 over the sine of 0. The sine of 0 is also 0. So 1 over 0 minus 1 over 0. In both cases here, as we approach from the right, these are going to become unbounded. So this is an indeterminate form of infinity minus infinity. So again, just like we did on the last one, we have to do a little bit of rewriting. And we want to turn this into either 0 over 0 or infinity over infinity. When we have an indeterminate form of infinity minus infinity, the best thing we can try first is just to combine our two fractions together. So let's get a common denominator. We'll subtract these two fractions, and let's see what we get. So this is the limit as x approaches 0 from the right. So my common denominator is going to be x times the sine of x. So multiplying the numerator and denominator of our first fraction by the sine of x, we have sine of x over x sine of x. And then this is going to be minus, now multiplying the numerator and denominator by x, we have x over x sine of x. And now bringing those two together, the limit as x approaches 0 from the right of the sine of x minus x all over x times the sine of x. So combining those two fractions together, now I think we're going to have an indeterminate form that does work with L'Hopital's rule. So if we try to plug in 0, the sine of 0 minus 0, and then 0 times the sine of 0. So this is going to simplify. We have 0 minus 0. The denominator, 0 times 0 is just 0. So we have this indeterminate form that works with L'Hopital's rule. So now using the rule, we can take the derivative of the numerator. This is going to be equal to, let's see, the derivative of sine is cosine. The derivative of x is 1. And then the derivative of our denominator, here we're going to have to use the product rule since we have x times the sine of x. So the first times the derivative of the second plus the derivative of the first times the second one. So now rewriting our limit using our derivatives, our new numerator is going to be the cosine of x minus 1, and our new denominator x cosine of x plus the sine of x. So now let's see if we can evaluate this by just plugging in 0. So the cosine of 0 minus 1. In the denominator, we're going to have 0 times the cosine of 0 plus the sine of 0. Cosine of 0 is equal to 1. So in the numerator, we have 1 minus 1. And then in the denominator, we have 0 times 1 and then plus 0. So we end up with 0 over 0 again. So we still have an indeterminate form, which means we have to keep going, but we can just use L'Hopital's rule a second time. So I'm just going to scroll down a little bit, and now we're going to take the derivative of the numerator and the denominator a second time. So the derivative of cosine of x minus 1. The derivative of cosine is negative sine. The derivative of 1 is just 0. And the derivative of our denominator, we have a couple terms here. So the derivative of x times the cosine of x plus the sine of x. So we got to use the product rule again. So the first times the derivative of the second. So x times the negative sine of x plus the derivative of the first times the second. That takes care of our first term. And then for the second term, the derivative of sine is equal to cosine. Now we can combine some like terms. So what we end up with here is negative x sine of x, and then cosine plus cosine, we get plus 2 cosine of x. So now rewriting our limit a second time, we have the limit as x approaches 0 from the right, and our numerator is going to be negative sine of x. And then in the denominator, we have negative x times the sine of x plus 2 cosine of x. And now hopefully this isn't in an indeterminate form anymore. So if we try to plug in 0, we have negative sine of 0. And then in the denominator, we have 0 times the sine of 0, and then plus 2 times the cosine of 0. So let's see what we get. The sine of 0, that's equal to 0. 0 times the sine of 0 is also 0. The cosine of 0 is equal to 1. So in the denominator, we end up with 2. So we don't have that indeterminate form anymore, and this simplifies down to 0. So we were able to evaluate that limit, which means all the way back up here at the top, our original limit, this is also equal to 0. So again, in this case, we ended up with an indeterminate form of infinity minus infinity, which is one that doesn't work with L'Hopital's rule. But we combined these two fractions together, we got a common denominator, and then we found the difference. And then this was an indeterminate form of 0 over 0, which allowed us to use L'Hopital's rule. We used L'Hopital's rule twice, and we were able to evaluate the limit, and then we found the original limit is equal to 0.